Biomechanics can be defined as the mechanics of the living systems. It has been suggested that biomechanical principles can be applied to distinguish between inner and outer forces. The study of biomechanics endeavors to determine optimal performance and enhance the learning process, especially regarding teaching methods of movement for increased efficiency and decreased risk of injury. Running is a learned skill, and it has been shown that at a given speed, muscular activity for the excellent runner is lower than that for the poor runner. Although treadmills are often used for training, they also can provide a means for a clinician or scientist to evaluate the biomechanics of running under controlled conditions. The style of running consists of 6 elements: the overall action, body angle, arm swing, foot placement, rear leg lift, and length of stride. Therefore, when minor differences in each element are accumulated, they will remarkably affect performance. The gait cycle is the basic unit of measurement in gait analysis. The gait cycle begins when one foot comes in contact with the ground and ends when the same foot contacts the ground again. These moments in time are referred to as initial contact with the ground. Ground reaction forces are generated in the vertical, horizontal, and rotatory plane in conjunction with weight acceptance during a stance phase. These forces, equal in intensity but opposite in direction to the forces experienced by the weight-bearing limb. Running requires the body to absorb continuous repeated impact forces that are initially absorbed by the foot and the ankle and then transfer up to the kinetic chain during the stance phase. The purpose of this study was to analyze the biomechanic work that is done by treadmills running exercise. The same method can be used by professionals to determine multiple injuries produced by several anatomical and biomechanical variables. The biomechanics of running has broad implications for the prevention of injuries. Runners are susceptible to overuse injuries, including heel pain, plantar fasciitis, Achilles tendonitis, sesamoitis, stress fractures, posterior tibial tendonitis. Several anatomical variables have been implicated as causes of overuse running injuries, including longitudinal arch structure of the foot, ankle range of motion, leg length discrepancies, and lower extremity alignment, and biomechanical variables such as excessive pronation, impact force, rate of force development, and other kinetic and kinematic factors. We recorded a video of the subject running using a treadmill in order to facilitate the recording in the same place. We made sure of capture the joints of interest in every moment while performing the exercise. The joints of interest were the hip, knee, and ankle. This video was analyzed in Biomechanics software. This is useful to obtain data as the position of the joints of interest in the choosing moment. Before I start working on the process previously mentioned, it is necessary to select the frame where the cycle is about to start. In this case, the select frame was number 24, because in it occurs that the right foot is completely on the ground. Then we obtain data from positions in X and Y axis. A second software was used. It is called Ginovea to obtain the angles in joint about knee, ankle, and hip. Once the data from Richmond was obtained, we calculated the proper time to be used in the calculus, and then the position was calculated. Figure 10 shows graphics of the positions in each axis, X and Y. In this graphic, we can see that the hip had almost a constant behavior. It presented varieties but too small. Knee position in X is the second joint with the greatest movement in this axis. The knee presents a movement that first goes back and then forth. This move explains why in the graphic the position line presents a curve down at first and then up. last position in x-axis was from the ankle. This joint has the greatest movement through both axes. The joint has a similar explanation as the knee. The difference with this one is that it has a larger range. Has the same movement going back and forth, but go farther than the knee, and that's why the curve from the ankle are more pronounced. On the other hand, we calculated the linear velocity and acceleration for both axes. About the hip, we deduct the velocity is increasing because it gains momentum in order to be able to move the leg. Otherwise, at the same time, the knee and ankle are decreasing their velocity, giving the hip the control in a way of putting it. Now, we observe linear velocity on y. If we compare the hip velocity from x and y axis, we can notice how in the second graphics the velocity oscillates around 1000 pixels per second, while in the x-axis it's around 500 pixels per second. For the knee, we observe an increase in the first seconds. The acceleration starts to decrease little by little until the last second where it goes up again. The behavior of the ankle acceleration remains constant at the first seconds. Then, the rest of the acceleration decreases because the velocity had a big change going down too. Finally, linear acceleration on y. During velocity, the joint with more drastic changes was the hip, and it is reflected in the acceleration graph because it has a bigger decrease than every other joint. Also, we determine the angular velocity and acceleration in both degrees and radian. The knee had a big change between the first seconds, then from 110 degrees to 157 degrees, producing a great peak. For angular acceleration graphic, each joint shows similar action as the velocity. The forces were calculated in two moments, during plantar flexion and dorsiflexion, as we can see in the table. Moments were calculated with two segments, hip-knee and knee-ankle. According to our results, our subject has a normally range of angle 65 of plantar flexion and 90 of dorsiflexion. On the other hand, results have shown a big force in dorsiflexion. The last two are a little bit higher than we expected. For this reason, it is important to keep studying carefully this case and visit a doctor to do more medical exams and rule out or prevent any injury or disease. Running efficiency and low rate of injury are associated with good lower extremity biomechanics. The influence of various surfaces on the load of the lower extremity, non-compliant floors, or unsuitable shoes is connected with the possibility of pain and injury. Correlation of the direction of the forces should, therefore, help to reduce unnecessary stress.